Good evening, everybody. As introduced, my name is John Banghoff. I work at the Weather Service in State College, so maybe one of the rare Eastern United States representatives here to maybe talk to you about the next big buzzword in the weather community, dew point bombs. I'll talk about what they are and why I believe they're one of the biggest targets of opportunity that we currently have. I want to thank my collaborators, Rob, Mike, Pat, and Max. It's really been a team effort throughout this process. So as you start, what's the motivation or problem or opportunity, depending on how you want to frame it? It's as follows. There are specific spring and some fall days as well where our weather models and therefore our Weather Service official forecasts badly overestimate minimum relative humidity or forecast the relative humidity significantly too high. And several years ago, our fire weather partners within Pennsylvania, so the Bureau of Forestry, as well as Allegheny National Forest, which exists in Northwest Pennsylvania, came to us and told us they often divide our minimum relative humidity forecasts by 2 in order to adequately prepare for fire weather potential. That's bad. That's really not a good thing that we want to do. So we've set out for the last several years to try to solve this issue for them. So dew point bombs, as we've defined them, are a dew point drop of 10 degrees in the afternoon, followed by then a rise of at least 5 degrees. So we're accounting for mixing and not just the advection of dry air. And here's a plot here from 2018 showing our Weather Service forecast versus the observations at Bradford in Northwest Pennsylvania. For keeping score, the dew point forecast was 31 degrees. The observation was 18 degrees, and that is a forecast error of 13 degrees. Bad by all accounts. Now, not to put the cart before the horse or anything, but the models aren't a whole heck of a lot better, which we'll talk about in just a little bit. And so this is something that we need to try to close that gap on. So we had a student volunteer a couple of years ago that looked at 110 dew point bomb cases from 2013 to 2021 in Pennsylvania, looking at ASOS sites, the red dots on the bottom left. Then looked at BuffKit soundings of NAM data to be able to see what the forecast was. And then we also used observations from Weather Underground to be able to sort of validate this overall process. And let's take a look at what we found. Well, the minimum observed relative humidity values on these so-called dew point bomb days were as follows. The main thing is that they were generally falling within the 20 to 30% range. Why that's relevant? If the observations were lower than our forecast, it's probably the case that on a lot of these days we were forecasting minimum relative humidities above 30%, which is not red flag warning criteria. And the relative humidities were actually falling into red flag warning criteria status, which is very problematic operationally. And so that's why this is such a problem. It often goes from not red flag warning criteria to red flag warning criteria, and we need to do a better job of forecasting it. Now, how far does the dew point drop? You can see a few cases that were close to dew point bombs, but not quite. But generally speaking, they were in the 10 to 20 degree Fahrenheit range. There were a few of these cases that were above 30, pushing even 40 or 50, which are the very extreme deep mixing cases. But in general, we're talking about a 10 to 20 degree drop in dew point. Now, putting it all together, we actually have some temperature contribution as well. And as we put this together and identify why the relative humidity misses so badly, the dew point is definitely the biggest contributor. You can see in the box and whisker plot there, generally on the order of 10 degree overestimation of dew point. But actually the temperature tends to be underestimated by a few degrees as well. And that all leads to, again, this minimum relative humidity error being 10 to 15 to 20% below what we're actually forecasting. Now, we believe that these errors are fixable. The problem is a change in the forecast for model guidance by 10 or 15 degrees or more is really going rogue. It's not something we do very often. And so we want to make sure that we're communicating well with our neighbors and getting good at this so that we don't cry wolf too much or totally go rogue unnecessarily. Now, let's look at some sounding guidance to be able to get a better picture of what's going on. A quick primer, dew point line is the black line on the left. Temperature is the line on the right. Generally, going to the left is cooler and or drier. Going to the right is warmer and or more moist. Now, our focus is going to be down in the boundary layer because that's where sensible weather occurs. And generally speaking, that's going to be looking at the top of the boundary layer, anywhere between 1,500 and 5,000 feet. And the two ingredients we want are first, weak or no inversion, such that we can mix deeply and tap into our second ingredient, which is very dry air just above the boundary layer. The combination of these two things is generally a pretty good recipe for some sort of decrease in dew point below guidance. As mixing occurs, you're going to see that drop down. And the big question is going to be, specifically on our sounding, how far left can that dew point line go? Or as I've called it, the burning question, pun intended, how far will the dew point drop? Is it going to be 5 degrees? Is it going to be 10? Is it going to be 15? Is it going to be 20? That matters a lot, and that's the part that we really need to dive into. Now, looking at soundings and picking them off is pretty labor intensive. It's very inefficient to go through a bunch of soundings, so maybe we can look at some broader geographic areas. The good news is the SPC mesoanalysis page provides some good insights for us. First, for the strength of the inversion, we can look at the low level lapse rate. Generally above 7 degrees Celsius per kilometer is going to indicate that we don't really have much of an inversion. And now, as far as moisture above the boundary layer, there's this interesting parameter, the LCL to LFC mean RH, giving us an idea of how dry it is just above the boundary layer. If that's below 30%, the combination of those two things is going to be pretty good. So now let's put this together and walk through a case study from April of 2021. We put together this dew point bomb viewer that you could look at if you want to. I've included the URL. 4 panels. The first is the surface analysis. There are identifiable synoptic setups for these that I don't have time to go over today. Our middle 2 panels are the variables that I talked about, low level lapse rate for inversion strength, and this LCL to LFC mean RH for dry air above the boundary layer. And then finally, this precipitable water and transport vector is just kind of another interesting proxy that we're kind of looking at a little bit more. So I was looking at this, there's really 2 areas we can identify with steep lapse rates and dry air. First in northeastern United States, the second one across the southeast. We have sufficiently steep low-level lapse rates and enough or low enough relative humidity in that layer. So as we look at these, we then go, we've identified the areas, then we can go look at some soundings. We've got Williamsport on the left, Scranton on the right-hand side in the afternoon. You can see for both of these, there's a weak or no inversion. There's plenty of dry air, at least sufficient dry air to be able to tap into to mix down to the surface. And we think this is pretty conducive to a dew point bomb. Well, saving some of the work and analysis that we went into, what happened? Well, there were dew point bombs in both areas at all of the locations where there are stars in our circled areas. So we found some success in identifying these with some reliability. Visualizing these are the same soundings at Scranton. You can see that the temperature overperformed by about 10 degrees, the dew point underperformed by about 26 degrees, and the relative humidity underperformed by 21%. This is definitely an extreme case, but still one that's possible. Williamsport was a little bit less significant, but we still saw a relative humidity area of 15%. And you can see if we had gone with the name, the forecast would have been 31% above red flag warning criteria, and then the observations were well below that. So that's a glimpse at sort of some individual cases, but let's look at some bulk model performance. The National Blend of Models is the flagship model that we use as a starting point in the Weather Service. And newsflash, it's not great at forecasting dew point bombs. And this is an example, a 1 a.m. forecast valid on this particular day for Williamsport in Northeast Pennsylvania. And you can see the errors for temperature, dew point, and relative humidity here on the right-hand side. And our relative humidity errors didn't start off very well, right? Relative humidity was already off by about 7%. But through the afternoon, it dropped even 14, 15, even 24% below guidance. So the NBM in and of itself is not particularly great. If we load that and go, we're not going to have a very good forecast. Well, let's look at some sort of more planar or field verification. Blue means the NBM was too low. Red means it was too high. So it underestimated temperature, overestimated relative or dew point, and therefore overestimated relative humidity. Well, we have from the NBM these 10th and 90th percentiles, 90th being sort of the worst case or the highest, 10th being the best case or the lowest in this case. And so what if we look at the 90th percentile temperature to get the ceiling for the temperature and the 10th percentile dew point to get the floor for the dew point and combine those to create a relative humidity value? Well, we see that looking at the bottom right, the combination isn't so bad. It's quite a bit better. Dew point still doesn't get quite low enough. Temperature actually overshoots a little bit, but the combination of those is a little bit better. So we're getting closer if we start employing some of the percentile guidance. Now, what if we look at some of the high resolution guidance? This is the high resolution ensemble forecast. Shown here on the left-hand side is the ensemble minimum relative humidity. So in this particular case, the HRF is saying that the minimum RH values could drop below 20% in Southeast Pennsylvania.
John, can
when
you
look at the observations, the dark reds are really below 20%. So it got the flavor, maybe not quite as widespread as what actually occurred, but still pretty decent. So the HRF shows some promise in this particular area. Don't have a ton of time, just want to highlight a couple other operational efforts. We put together a one-pager for forecasters front and back to be able to refresh on the process for these. We put together some procedures in AWIPS to be able to forecast lapse rate and moisture in the or above the boundary layer for our forecasters. And then we've also prototyped this spot forecast monitor to not only monitor the current forecast relative to current conditions, but what our forecast was at 4 or 5 a.m. when we're doing spot forecasts. I believe I'm out of time. I'll put up my summary slide here. We'd be happy to chat offline about this. It's a big passion. I've got QR codes to both a dew point bomb guide and a more extensive set of slides from this presentation. Thank you so much.
Thank you, John.